Welcome to the deep dive. We're here to take really complex source material, try and strip away some of the jargon, and hopefully get straight to the knowledge you need.
That's the plan.
Today, we are tackling, frankly, a massive problem. It's this foundational issue that's kept global finance and, truly decentralized tech apart for years. Scalability and compliance.
Exactly. We're diving deep into something called KeetNet. It's a system being put forward by an engineering company, Keeta, and they're positioning it as, well, a potential bridge here.
Right.
Their 2025 white paper, which is our main source today, doesn't really hold back. It describes KeetNet as a cloud-scale and cloud-native solution, and it's specifically engineered, they say, to solve these huge scalability and compliance hurdles that have, consistently blocked big banks from really moving digital value onto decentralized ledgers.
And the claims they're making are, well, they're pretty bold. We're talking unprecedented linear scaling, transaction throughput numbers that would make something like Bitcoin look incredibly slow.
Like a crawl, yeah.
And then there's the really crucial part, especially for finance. Built-in infrastructure for regulatory stuff. Things like know your customer, KYC, and anti-money laundering. AML.
So our mission today really is to dig into the engineering and see if it actually backs up these massive claims.
Yeah, Keeta is essentially trying to build that missing link between the traditional, heavily regulated financial world and this new distributed ledger technology, or DLT. And you're right, it's been almost impossible to build this bridge so far.
Why is that fundamentally?
Well, traditional finance demands transactions that are audited, certain, and incredibly fast. You need that finality. But early DLT, its focus was almost entirely on achieving absolute decentralization, and often that meant sacrificing performance speed and critically suitability for regulated environments.
Okay, so let's try and unpack KeetaNet. We'll break down their architecture by looking at three main scaling mechanisms they talk about. First, there's this unique data structure, a hybrid-directed acyclic graph, or they call it a virtual DAG.
Second, a really different way of approving transactions. Client-directed two-step validation. Sounds interesting.
It is.
And finally, the foundation it's all built on, their cloud-scale architecture, using things like serverless processing to sort of redefine what capacity even means in this context.
That's a good roadmap. It hits the key innovations.
All right, before we jump into KeetNet's breakthroughs, maybe we should level set a bit. We keep saying distributed ledger technology, DLT. We generally know it's like a shared record book. But what really makes DLT different from, say, just a regular synchronized database that multiple people can access?
Yeah, that's a good place to start. The absolute key difference is synchronization among mutually distrusting parties. That's the core concept.
Okay.
So the DLT is a very specialized kind of distributed system. Its job is to maintain a single consistent ledger, that record book across potentially many nodes, many computers. And crucially, it works even if none of those participants actually trust each other.
Right, no central authority needed.
Exactly. And it typically has three main parts. There's the database itself, which holds the ledger that could be a blockchain or some other way of storing the data. Then there's the network connecting everyone. And finally, the consensus mechanism. That's the set of rules that determines which updates to the ledger are valid, which ones get accepted.
And the most famous type of DLT, the one everyone's heard of, is blockchain.
Correct. A blockchain system is really defined by how it structures that data. It's a sequential chain of records, or blocks. Each new block is cryptographically tied to the one before it using something called a hash.
Like a digital fingerprint of the previous block?
Precisely. And that hash linkage is what guarantees integrity and immutability. If you try to tamper with any record anywhere in the chain, that link breaks. The math just doesn't add up anymore and everyone can see it.
Okay, so that's the integrity part, but why use this complex chain instead of a normal database?
It comes back to that core advantage. Enabling updates, changes to the ledger state from multiple entities who don't trust each other without needing a central gatekeeper. You don't need one bank or one company controlling everything. The consensus mechanism itself acts as that distributed gatekeeper, validating every proposed change against the rules everyone agreed on beforehand.
That makes sense. That benefit, the trustless integrity, is powerful. But this model historically has led straight into what people call the scalability crisis. If a system can't handle, millions or even thousands of transactions per second smoothly, its actual usefulness for something like global finance is basically zero. Why has scaling DLT been such a persistent problem for early systems like Bitcoin or even Ethereum's main layer?
It almost entirely boils down to one thing: state management. managing the state of the system.
What do you mean by state exactly?
State is just the current status of everything the ledger tracks. So the balance of every single account, the complete history of every transaction, who owns what token, all of that collective information is the state. Now, if you have a stateless system where each request is totally independent, doesn't rely on past requests, scaling is relatively easy, you just throw more servers at it.
Like browsing a website, each page load is mostly independent.
Right. But blockchains maintain this incredibly complex shared state. And every time someone wants to change that state, send money, interact with a contract, it requires intense coordination among all the nodes participating in the network to make sure everyone agrees on the new state.
Yeah.
And as transaction volume shoots up, that coordination becomes a massive bottleneck. Everyone has to agree on the exact order, the exact outcome.
And this leads us almost inevitably to talking about distributed systems constraints, specifically the CAP theorem. It sounds technical, but it's fundamental. Can you break down Brewer's theorem simply for us? Because it feels like KeetaNet has to operate right within these constraints.
Absolutely. CAP theorem is crucial here. It basically defines an unavoidable trade-off you face when designing any distributed system. It stands for consistency, availability, and partition tolerance.
Right. PAC.
Exactly. And the first thing to understand is that partition tolerance, P, isn't really optional for a global DLT. You must assume the network will sometimes break, that groups of nodes might get temporarily disconnected from each other. The system has to keep operating correctly even during these network partitions.
So P is mandatory. You have to deal with network splits.
Correct. Which means, given P is a must-have, you're forced into a direct trade-off between the other two, consistency C and availability A.
Okay, so what's the trade-off? Define CNA for us.
Consistency C means that every node in the network that can talk to each other has the exact same unified view of the ledger state at the exact same moment. If I query the ledger from node A, I get the same answer as querying node B simultaneously. It's about a single unified truth.
Got it. And availability?
Availability A means the system is always operational and responsive. If I send a transaction request, I get a response back, confirming whether it succeeded or failed. The system keeps working, keeps processing requests, even if some nodes are down or temporarily cut off due to a network partition.
Okay, so you want the network to keep running, availability,
Yeah.
but you also want everyone to agree on the data, consistency. And CAP says you can't perfectly have both if the network splits.
That's the crux of it. You have to lean one way or the other when designing the system. Bitcoin, for example, famously prioritizes C over A.
How so?
It prioritizes absolute immediate consistency. Every single transaction must be globally confirmed and put into a strict sequential order agreed upon by everyone. That's why transaction finality can take up to 60 minutes. It takes time to ensure that global consensus and ordering. Bitcoin maintains a state that is always 100% agreed upon by the majority, but it sacrifices availability and speed, especially when the network gets busy or partitioned. Transactions might get delayed significantly.
So, KeetaNet, aiming for banking speeds, sub-second transactions, has to navigate this differently. They need partition tolerance, obviously. They need very high availability. You can't have a bank system go offline. But they also can't sacrifice the security that consistency provides, right? You need accurate balances.
Exactly. They need to find a sophisticated way to manage state that gives them the high availability and speed required for finance, without compromising the integrity and correctness that comes from consistency. It's a very fine line to walk.
Okay, that really sets the stage for understanding the limitations KeetaNet is trying to overcome. We've seen this rigidity problem in older systems. Bitcoin's block size war is a famous example, years of fighting just to change a fundamental parameter. It required this massive, difficult community consensus. KeetaNet claims it's built for better extensibility. How does their architecture actually try to prevent these kinds of future protocol wars?
They tackle this on two fronts, really. The technical design itself and the governance model.
Let's start with the tech. How is it more flexible?
Well, a big issue with some early blockchains was using fixed-length constraints for data fields in the blocks. Like maybe they defined an operation code using only 8 bits, thinking that's plenty. But then years later, you need more operation types, or a new cryptography standard requires a much larger key size.
And you're stuck. Changing that fixed length breaks everything. Needs a hard fork.
Precisely. It forces these really difficult, disruptive upgrades where everyone has to switch over simultaneously. KeetaNet seems to have learned this lesson. They use more extensible data formats from the start. The white paper mentions using things like ASN.1 Abstract Syntax Notation 1.
What does that do?
ASN.1 is a standard designed specifically for defining data structures that can evolve over time. It allows fields like the block structure version number, different types of operations, or identifiers for cryptographic algorithms, OIDs, to grow or change without breaking compatibility with older versions. They also mention using big integers for operation types, giving them essentially limitless room for future expansion.
So it's about future-proofing the data structures themselves, thinking ahead to things like post-quantum cryptography, PQC.
Exactly. PQC often involves larger key sizes or different signature schemes. A system built with extensible formats can potentially adopt these new standards much more easily down the line without needing a massive, painful protocol overhaul and community split every time cryptography advances. It builds in adaptability.
Okay, so the system's technically designed to be flexible, but flexibility can be dangerous if it leads to centralization, right? How does the governance model ensure this technical adaptability doesn't just mean a few powerful players can change the rules whenever they want? They mention this representative authority structure.
Right. The governance is key to maintaining decentralization alongside that flexibility. They use a delegated proof of stake model, DPoS.
Explain DPoS quickly.
In DPoS, regular users who hold the network's base token delegate their voting power, derived from their token balance, to specific entities called representatives. Crucially, the users still own their tokens. They just lend the voting weight.
Okay, so users choose who gets to vote on network matters.
Yes, and these representatives are the ones who actually vote on things like protocol upgrades, changing fee structures, or adjusting parameters like block size limits. This representative authority means you don't need every single user or every node operator to actively participate in every single governance decision.
Which avoids the gridlock we saw in Bitcoin's block size debate.
Hopefully, yes. It allows the network to adapt more quickly and efficiently because decisions are made by a designated accountable group chosen by the users. But importantly, that delegation is revocable. If users don't like how a representative is voting or behaving, they can withdraw their delegation and give it to someone else. So the ultimate power, the voting weight, still resides with the broad base of users, ensuring decentralization isn't lost.
All right, let's shift gears to the really innovative parts. The core architecture that supposedly allows these, frankly, still mind-boggling 13 million TPS claims. It seems to start with what they call the cloud scale paradigm shift. Why is building a DLT using cloud-native, maybe even serverless tech, fundamentally different from how traditional blockchains tried to scale?
This is probably the most fundamental architectural shift they're proposing. It's a complete change in philosophy. Traditional blockchains, when they thought about scaling, mostly focused on optimizing the individual validator node.
Like trying to make one computer run faster.
Exactly. Trying to cram more processing power, more cores, better multi-threading, all within a single machine running the validator software. It's like trying to scale up a big monolithic application on a single powerful server. You inevitably hit fiscal limits pretty quickly. It's vertical scaling.
And KeetaNet just flips that entirely.
Completely. They go for horizontal scaling. KeetaNet isn't designed as one big program running on one big machine. It's conceived as a highly distributed architecture, spread across potentially thousands or even tens of thousands of independent computing units. Think more like modern cloud microservices.
Okay. How does that work in practice?
They made a key decision. Build on top of standard, common, and incredibly scalable web protocols. Things we use every day, like HTTPS for the consensus actions and WebSockets for the peer-to-peer network traffic.
Not some custom bespoke blockchain network protocol.
Right. By using standard web tech, they can directly leverage the massive scalability and elasticity built into existing cloud infrastructure. Think services like AWS Lambda or Google Cloud Run. These are serverless computing platforms.
Okay, explain that elasticity part simply. Why is using something like AWS Lambda inherently more scalable than just buying a ridiculously huge server?
Let's use an analogy. Imagine your DLT network is like a giant highway system. On a quiet Sunday night, maybe there's very little traffic. You only need a few lanes open.
Makes sense.
But come Monday morning rush hour, maybe triggered by a market opening or a big event, the transaction volume suddenly spikes, maybe by 1,000x or more. A traditional system would either collapse under that sudden load, or you'd have to permanently pay for and maintain enough massive servers to handle that absolute peak moment, even though they sit idle 99% of the time.
Which is incredibly inefficient and expensive.
Totally. Serverless architecture gives you near-instant elasticity. When that traffic spike hits KeetaNet, the underlying cloud platform can automatically, almost instantly, spin up hundreds or thousands of independent, temporary processing instances, these Lambdas or cloud-run instances, specifically to handle that surge.
So it scales up on demand.
Exactly. The computation gets distributed immediately across a vast number of machines for exactly as long as it's needed. And when the surge passes, it scales back down automatically. This is how they can claim unbounded linear scaling. The system's capacity effectively scales linearly with the amount of cloud hardware you're willing to provision or that the cloud provider makes available. It's not limited by a single machine's capability.
That sounds incredibly powerful for both performance and cost efficiency. But
Yeah.
managing that kind of massive parallel processing, surely that requires a completely different way of thinking about the data structure itself. Which brings us to their virtual directed acyclic graph, or virtual DAG. Can you explain this? I really want to hammer this point. What does it mean that there is no single monolithic blockchain in KeetaNet?
It's a radical departure. It means throwing out the idea of a single, long queue that every single transaction has to wait in. That single queue is the definition of total ordering.
Total ordering.
Yes. Systems like Bitcoin or consensus mechanisms like Tendermint enforce total global ordering. Every transaction, no matter how unrelated, has to find its precise sequential place in that single global chain. Transaction B cannot happen until transaction A is fully confirmed and written down, even if A and B have absolutely nothing to do with each other. This global sequencing requirement is the bottleneck.
Okay, so how does KeetaNet avoid this? What's the DAG structure?
It's built around individual accounts. The white paper states, and this is crucial, that each account forms the basis of its own ordered blockchain. Think of it like this. My account has its own mini blockchain, tracking my transactions in sequence 1, 2, 3, and so on. Your account has its own mini blockchain, tracking your transactions in order.
So lots of little chains instead of one big one.
Exactly. Now, when I send tokens to you, that specific transaction creates a kind of virtual link between my account's chain and your account's chain. It references the last state of my account and creates a new state for your account. Collectively, all these individual account chains, plus all the virtual links created by inter-account transactions, form this wider structure that mathematically resembles a directed acyclic graph, or DAG. It's directed because transactions flow from sender to receiver, and acyclic because you can't have circular dependencies, you can't spend money you haven't received yet.
So the key insight here is that transactions that don't directly depend on each other can happen at the same time. If I send money to Alice and you simultaneously send money to Bob, those can be processed in parallel.
Precisely. Because my transaction only needs to know about my balance and Alice's address, and your transaction only needs to know about your balance and Bob's address. They don't conflict. They don't need a global lock on the entire network state to proceed. KeetaNet uses what's called partial ordering. Transactions are only ordered relative to the specific accounts and constraints they absolutely must respect.
Instead of forcing everything into one single file line.
Exactly. And since the vast majority of financial transactions at their core only involve two parties, a sender and a receiver, most of them can be processed in parallel across this distributed cloud-native architecture. This shift from total ordering to partial ordering is the fundamental reason they can realistically target such incredibly high throughput numbers where totally ordered systems fundamentally cannot.
Okay, the scalability picture is becoming much clearer now. The cloud infrastructure provides the raw horsepower, and the virtual DAG structure lets them actually use that horsepower in parallel. Now let's talk about how they ensure these parallel transactions are actually valid and final. The consensus mechanism. They use DPoS, we covered that, but the validation process itself is this client-directed two-phase voting, which they say is modeled after optimistic concurrency control, or OCC. What is OCC in simple terms?
Optimistic concurrency control. It's a database strategy, actually. The core idea is assume conflicts between transactions will be rare. So don't spend a lot of time and resources locking everything down beforehand. Just let transactions proceed optimistically.
Hope for the best.
Sort of. Let them proceed, but track what resources they read and what they intend to write. Then, right at the very end, before making the change permanent, check if any other transaction has changed the data you relied on since you started. If there's a conflict, one of the transactions has to fail and maybe retry. If there's no conflict, commit the change.
Okay, so assume it'll work, but verify at the last second. How does Keeta apply this, and what does client-directed mean here?
The client-directed part is critical. It means you, the user initiating the transaction, are the one driving the process. You don't just throw your transaction into a public pool and hope for the best.
Right.
So here's the two-phase process. Imagine you want to send a large amount of tokens. You, the client, Directly contact a sufficient number of representatives the validator's chosen via DPoS using secure HTTPS connections. This is phase 1, requesting temporary votes.
Okay, what happens then?
Each representative you contact looks at your transaction right now. Do you have the funds? Is the signature valid based on the current state they see? If everything looks good at that moment, they issue a temporary vote back to you. The goal of this phase is simply to establish that an initial quorum of validators agrees your transaction could be valid. Think of it maybe like a bank teller confirming, yes, the funds are currently available in your account.
But that's just temporary. What stops someone, maybe even you, from trying to spend that same money again in a different transaction between getting those temporary votes and the final confirmation? The double spend problem.
That's exactly what the two-phase separation is designed to prevent, using that OCC logic. Phase 2 is about permanent votes. Only those representatives who successfully issued a temporary vote in Phase 1 are then asked by you, the client, to issue a permanent vote.
I see.
Now, when they go to issue that permanent vote, they perform a final check. Has the state of your account changed since they issued the temporary vote? If another transaction slipped in and already spent those funds, the check will fail. That representative will detect the conflict because the account state changed unexpectedly and will refuse to issue the permanent vote for your transaction.
So the OCC check happens right before the final commitment.
Exactly. The two-step process ensures that the quorum is fully established and the state hasn't changed conflictually before the transaction gets final approval. It protects against race conditions and double spends by verifying consistency at the critical moment of finalization.
Okay, that makes sense. And once a transaction successfully gets enough permanent votes, the data isn't just broadcast piece by piece, right? They bundle it into something called a vote staple.
Yes, the vote staple. This is an efficiency optimization. Instead of broadcasting lots of individual votes and block fragments across the network, the client gathers the successful permanent votes and the resulting block data into a single, consolidated package, the staple.
And sends that out.
And that staple is what gets broadcast efficiently to the rest of the network for storage and replication. Importantly, the staple acts like an atomic unit. It's all or nothing. If any part of the staple is found to be invalid by the wider network, maybe a rule violation, an incorrect sequence number, evidence of a double spend attempt that somehow got through the voting, the entire staple is rejected. It ensures atomicity and consistency for that whole bundle of updates.
This whole client-directed two-phase stable-based approach, it feels like it's specifically designed to solve one of the biggest headaches in older blockchains.
Oh.
The mempool, the transaction waiting room.
Absolutely. It's a direct answer to the chaos of traditional mempools.
Explain that chaos. Systems like Bitcoin or Ethereum, what's the problem with their mempools?
Traditional mempools are essentially public, unordered waiting rooms. You submit your transaction, and it sits there, visible to everyone, waiting for a miner in PowerView or validator in Pyrrhus to pick it up and include it in a block. It's probabilistic you don't know if or when it will get picked.
And this leads to issues like front-running.
Exactly. Because everything's public, sophisticated bots can see your pending transaction, maybe a large trade on a decentralized exchange, and submit their own transaction with a higher fee to get processed first, profiting from the price movement your trade will cause. This is sometimes called the dark forest problem in Ethereum, a predatory environment. Plus, there's just the uncertainty for the user and the massive network traffic from broadcasting all these pending, unconfirmed transactions everywhere.
So how does KeetaNet's client-directed approach avoid this dark forest?
But fundamentally changing how transactions are distributed. In KeetaNet, transactions or blocks that haven't successfully completed that two-phase voting process and achieved a final quorum are simply not broadcast widely across the peer-to-peer network. They aren't exposed publicly in that pending state.
Only the final result is shared.
Precisely. Only the fully accepted, validated vote staples representing committed, final state changes are broadcast to the network for recording. This transforms the experience for the client. Instead of throwing a transaction into a chaotic, probabilistic pool, you follow a clear, linear pipeline. Request temporary votes, request permanent votes, a simple staple, receive confirmation.
Much more deterministic.
Yes, the client gets near-instant feedback on success or failure. Confirmation times become predictable and typically sub-second. And the network itself is massively relieved of the burden of propagating and managing millions of uncertain, pending transactions. It cuts down on noise and complexity enormously.
Okay, we've established a plausible path to high speed and throughput. But for the target audience banks, regulated institution speed is basically irrelevant if you can't meet strict compliance requirements. KeetaNet claims built-in KYC and AML infrastructure. But we're always told you absolutely cannot store personally identifiable information, PII, on a public or even permissioned ledger. So how do they square this circle? How can KeyNet handle compliance without putting names, addresses, or social security numbers directly onto the blockchain?
This is potentially one of the most elegant parts of the design,
Mm.
and it relies on a clever separation of concerns. The source material is very clear on this. No PII is stored on the ledger itself. That's rule number one.
Okay, so how do they verify identity then?
They leverage existing, standardized, globally recognized technology. X.509, public key infrastructure, or PKI.
PKI, that's the system the entire web uses for security, right?
Right.
For SSL/TLS certificates that make HTTPS connections secure.
Exactly the same underlying technology. Think about how a website gets an SSL certificate. A trusted third party, called a certificate authority or CA, verifies the identity of the website owner, offline through documentation. Then the CA issues a digital certificate that cryptographically binds the website's public key to its verified identity, like its domain name. Your browser checks this certificate to know it's talking to the real website.
Okay, I follow that. How does that apply to a user's account on Keeta?
It's a very similar model. A user, or more likely an institution onboarding users, would work with a trusted CA, maybe a government agency, a regulated financial institution, or a specialized identity provider. This CA performs the necessary KYC/ML checks off-chain, verifying the user's real-world identity according to regulations.
So the compliance check happens outside Keeta.
Yes. Then, the CA issues an X.509 certificate that cryptographically links the user's public key, which controls their KeyNet account, to some representation of their verified status. Crucially, this certificate itself doesn't need to contain sensitive PII like your name or address. It might just contain an identifier or attributes confirming you passed certain checks.
And this certificate is somehow linked to the account on the ledger?
Correct. The KeyNet account can be associated with this X.509 certificate, which is signed by a CA the network trusts. The ledger itself might only store a reference to this certificate or perhaps the certificate's public information, but not the underlying PII used for the initial verification.
So when I make a transaction,
The network can check your account's associated certificate. It verifies the signature from the trusted CA. This allows the network to confirm, with very high cryptographic assurance, that the entity controlling this account's private key has passed the necessary off-chain compliance checks by a recognized authority.
so it proves compliance status without revealing personal details on the chain.
Exactly. It perfectly separates the proof of identity verification, which happens off-ledger via the CA, from the proof of key control and transaction authorization, which happens on-ledger. This separation is the absolute key to enabling regulatory compliance in a decentralized environment without compromising user privacy by putting PII on an immutable ledger.
That's actually quite clever. It defines very clear trust boundaries. The user trusts the CA for verification. The network trusts the CA's signature on the certificate. Can this PKI system do more than just a simple yes/no on KYC status?
Oh, absolutely. The potential is much broader. It opens the door to decentralized, user-controlled attribute verification. Using more advanced cryptographic techniques, possibly things like ECEs, elliptic curve integrated encryption scheme, or special hashing methods mentioned in the context of identity, you could prove specific things about yourself without revealing the raw data.
Like what, for example?
Well, imagine a CA verifies your email address. Using crypto, you could potentially prove to a specific service provider on KeyNet, yes, I possess an email address verified by CAX, without actually revealing your email address on the ledger, or even to the service provider directly. Or maybe prove, I reside within jurisdiction Y for regulatory purposes, again, without revealing your precise home address publicly. The user controls what attributes get proven and to whom.
This idea of fine-grained control over identity attributes seems to lead naturally into KeyNet's extensible permission system. This sounds critical for managing regulated assets, like maybe a bank-issued stablecoin where only certain verified customers can hold or transact it. How does KeyNet actually enforce these kinds of granular rules?
You're right, it's vital. They manage this using an access control list, or ACL, which is stored as part of the ledger state. This ACL essentially defines a set of rules. Who is allowed to do what, with which specific asset, or to which specific account. Having this built into the core protocol is pretty significant for regulated use cases.
How does the system figure out which rule applies if there are potentially many rules?
It uses a clear hierarchy based on specificity. When an action is attempted, say, user A tries to send token B to user C, the system checks the ACL, starting from the most specific possible rule that could apply. For example, is there a rule specifically for user A interacting with token B targeting user C?
Okay.
If not, it looks for a slightly less specific rule, maybe just about user A sending token B to anyone, then maybe a rule about anyone sending token B. It continues down this path from most specific to least specific, perhaps ending with default network-wide permissions. The key is, the first matching rule it finds, starting from the most specific, is the one that applies, and it overrides any less specific rules further down the hierarchy.
So you can set very precise overrides. A bank could say, generally, anyone can hold our stablecoin except for accounts without a verified U.S. resident certificate, and that specific rule would override the general permission.
Exactly that. It allows for very nuanced policy enforcement, which regulators demand.
The source material also distinguishes between base permissions and external permissions. What's the difference there? Is it important?
It's a useful distinction. Base permissions are core, fundamental rights defined and understood directly by the Keeta Network protocol itself. Things like owner, who controls the account, send on behalf, allowing delegated sending, or token admin supply, ability to mint or burn a specific token. The network consensus rules verify and enforce these base permissions directly.
Okay, those are built-in system rights. What are external permissions?
External permissions are essentially just arbitrary flags or labels that can be attached to accounts or tokens. They don't have inherent meaning to the core Keeta Network protocol. Their meaning and enforcement are defined by external logic, perhaps within a smart contract or an off-chain application built on top of Keeta Network. The network stores them, but doesn't necessarily act on them directly.
So base permissions are for core protocol security. External permissions are for application-level logic.
That's a good way to think about it. And both types, according to the material, use efficient bit field encoding, which just means they can pack a lot of different permission flags into a small amount of data storage on the ledger.
Let's use a concrete example to really understand the precision and security here. The white paper uses an example about changing the owner base permission for, say, a critical storage account. Why is it absolutely essential that granting ownership to the new owner and removing it from the old owner happen atomically within the same vote table?
Yes, this hits on a classic distributed systems consistency problem. It's about preventing dangerous intermediate states. The owner permission is fundamental. It represents ultimate control. For safety and security, the system must enforce a rule. There must always be exactly one address holding the owner permission for any given account at any point in time.
Not zero, not two. Always one.
Always exactly one. Now, imagine you trying to transfer ownership in two separate steps, two separate transactions or staples. Step 1, grant owner to the new address. Step 2, remove owner from the old address.
What could go wrong?
Well, what if step 1 succeeds, but step 2 fails for some reason? Maybe network lag, maybe a temporary node issue. You briefly have a state where two addresses have owner permission, a massive security hole. Or what if step 2 happens first, removing the old owner, but step 1 fails? Then you'd have zero owners. The account becomes permanently locked and inaccessible, its assets lost forever.
Both disastrous outcomes.
Totally. By requiring that both actions, the removal from the old owner and the granting to the new owner, must be bundled together in the same vote staple, Keeta Network ensures the transition is atomic. It happens instantaneously from the network's perspective. The state goes directly from owner A has control to owner B has control, with no risky intermediate states possible. That staple acts like an unbreakable escrow, ensuring the transfer happens correctly or not at all.
That's incredibly robust. Okay, shifting slightly to broader security concerns. How does this architecture defend against some of the classic attacks that plague decentralized networks? Let's start with the Sybil attack, where one attacker creates tons of fake identities or nodes to try and overwhelm the consensus or gain undue influence.
The primary defense against Sybil attacks seems to tie back directly to that X.509 PKI system we discussed for compliance.
How so?
Because, according to the material, nodes acting as representatives, the ones doing the voting, are required to certify their network endpoints using these X.509 certificates.
Yeah.
And these certificates, remember, are issued by trusted CAs that perform real-world identity verification.
So you can't just spin up a million anonymous nodes easily.
It's exactly. To launch a large-scale Sybil attack aimed at controlling consensus, an attacker wouldn't just need a lot of computing power or stake. They'd need to acquire a huge number of unique, valid X.509 certificates from trusted authorities, each tied to some form of verified identity. The cost, complexity, and logistical challenge of doing that legitimately becomes a massive economic and practical deterrent. It adds a strong layer of identity-based resistance on top of the economic stake required by DPoS.
That makes sense. Okay, what about just flooding the network with useless but technically valid transactions? Denial of service, DES, or spam attacks aimed at clogging the system.
There seem to be multiple layers of defense here. First, that two-phase voting process acts as an initial filter. Transactions that are obviously invalid or malformed likely won't even get temporary votes, so they get dropped early before consuming significant network resources or hitting the P2P layer.
But what about just millions of tiny, valid transactions designed purely to annoy or overload?
Right. The legitimate spam problem.
Yeah.
The protocol appears to give representatives tools to combat this. They have the discretion, based on observed network conditions or suspicious patterns of activity, to dynamically impose much higher transaction fees for certain types of transactions or from certain sources. Or, in extreme cases, they could potentially decline to issue votes altogether for activity that clearly looks abusive, even if each individual transaction seems valid on its own.
So economic deterrence and validator discretion.
Yes. Plus, a more fundamental point. Because the core consensus voting actions happen over standard protocols like HTTPS, KeetaNet can potentially benefit directly from existing highly sophisticated commercial-grade anti-DDoS protection services offered by cloud providers. They don't necessarily have to reinvent all the DOS mitigation techniques from scratch. They can leverage battle-tested internet infrastructure.
Okay, we've walked through the architecture, the consensus, the compliance, the security. It all sounds coherent. But now we have to circle back to those performance numbers because, honestly, that 13 million TPS figure still sounds almost fantastical. The white paper provides benchmark results. What were the conditions for that test?
Yeah, the numbers are definitely eye-catching. The white paper reports achieving a maximum transaction per second throughput of 13 million TPS in their benchmark tests. It's important to note the context. These tests specifically utilized Google Cloud Spanner as the underlying ledger database.
Why Spanner?
Spanner is Google's globally distributed, strongly consistent database service. Using something like Spanner was likely necessary to handle the sheer scale of distributed state management required to actually realize that level of throughput across potentially thousands of parallel processing units. The bottleneck, if you achieve that level of parallel execution, shifts to how fast you can consistently read and write the shared state. Spanner is designed for exactly that kind of high-consistency, high-throughput distributed workload.
Okay, so 13 million TPS achieved using a high-end distributed database in a test environment. Let me play devil's advocate. Is that a realistic, sustainable rate, or more like a peak burst speed under ideal lab conditions? And where's the catch? If it's really that much faster than everything else, why isn't everyone doing it? What's the potential weak link?
That's the right question to ask. The paper presents it as the maximum throughput achieved, likely representing the system operating at full parallel capacity under optimal conditions. Whether that's sustainable minute by minute in a real-world deployment with unpredictable traffic patterns is always a fair question for any benchmark. However, the reason they can even claim such a number isn't about some magic coding trick. It's the fundamental architectural shift we discussed.
Away from total ordering.
Exactly. The bottleneck in older systems isn't usually the code execution speed itself. It's the sequential dependency imposed by total global ordering. Every transaction has to wait its turn in that single line. KeetaNet, by using the virtual DAG impartial ordering, fundamentally removes that sequential bottleneck for the vast majority of transactions.
So the potential TPS scales with the degree of parallelism you can achieve.
Precisely. If 99% of transactions don't conflict, they can theoretically be processed in parallel across thousands of those serverless compute units we talked about. The 13 million TPS figure is essentially a statement about the potential parallelism unlocked by the DAG structure, coupled with the elasticity of the cloud-native design. The potential catch or challenge isn't necessarily a single weak link, but the complexity of managing that highly distributed state consistently and the reliance on sophisticated underlying infrastructure like Spanner to handle the database load at that scale. And crucially, the white paper emphasizes they achieve this potential throughput without sacrificing transaction architect. Latency finality remains sub-second.
Okay, let's put that 13M TPS figure, even as a theoretical maximum, into stark context. The sources provide a comparison table, Table 1 in the white paper. How does it stack up against major existing systems?
The difference is pretty dramatic. Bitcoin, using proof of work, you're looking at around 7 TPS on average. And critically, finality knowing your transaction is irreversible takes about 60 minutes. Scaling relies heavily on Layer 2 solutions like the Lightning Network, which operate off the main chain.
Okay, 7 versus 13 million. Huge gap. What about Ethereum?
Ethereum Layer 1, now using proof of stake, it's a bit faster, maybe around 15 TPS. Finality is quicker than Bitcoin, around 6.4 minutes, but still far from instant. And again, significant scaling for Ethereum relies almost entirely on external layer 2 solutions, things like rollups or state channels.
So both major incumbents are orders of magnitude slower on their base layer and need separate systems for real scale. Are there any faster modern blockchains for comparison?
Yes, the table mentions newer systems designed specifically for higher throughput. SUI, which uses a form of DPoS and DAG concepts, is cited at around 300,000 TPS. Aptos, using proof of stake, around 160,000 TPS. These are impressive numbers, way beyond Bitcoin or Ethereum L1.
But still 160K, 300K, compared to a claimed 13 million for Keeta.
It's a difference of scale, absolutely. Keeta is claiming throughput potentially 40 to 80 times higher than even these modern high-speed competitors, and achieving it on the base layer while maintaining that crucial combination of strong consistency and sub-second finality that regulated financial applications absolutely require.
Assuming the architecture holds up to these claims in real-world deployment, this combination of massive throughput, low latency, strong consistency, and built-in compliance infrastructure obviously opens up some significant potential use cases. The first one seems obvious: blockchain banking.
Yes, this feels like the primary target market.
Ah.
Keeta seems almost tailor-made for regulated financial institutions that want to leverage DLT. Why? Because that granular permissioning system tied to the X.509 certificate infrastructure allows them to enforce the strict rules they operate under. For example, a bank could issue a fiat-backed stablecoin on Keeta and configure its permissions such that only users whose accounts are linked to a certificate, verifying they've passed KYC-AML with that specific bank, or perhaps confirming they reside in an allowed jurisdiction, can actually hold or transact that stablecoin. This allows the bank to operate a digital asset on a decentralized ledger while remaining fully compliant with global financial regulations like AML and sanctions screening. That's been the missing piece for many institutions.
Beyond just stablecoins, the system also allows users to create their own tokens and supports native atomic swaps between these tokens without needing a centralized intermediary. What does that enable?
That functionality positions Keeta as potentially becoming a kind of cryptocurrency central, or maybe a network of networks. It could serve as a highly efficient layer 2 scaling and settlement solution for many other cryptocurrencies.
How'd that work?
You could have wrapped versions of other assets like wrapped Bitcoin or wrapped Ether represented as tokens on Keeta. Users could then trade these wrapped tokens on Keeta at incredibly high speed and low cost, leveraging its throughput. Furthermore, the native atomic swap capability means users could directly exchange different user-created tokens on Keeta. Perhaps swapping a token representing a stock for a stablecoin securely and instantly, without needing to trust a centralized exchange or intermediary for the swap itself. It could become a foundational compliant settlement layer for a wide range of digital assets.
Interesting. And finally, let's revisit digital identity management. We touched on the PKI system for compliance, but what are the broader implications if this kind of system gets adopted beyond just finance for everyday digital life?
The implications could be quite profound, primarily because it shifts the focus towards user control over their own identity attributes. The PKI infrastructure isn't limited to banks. Imagine other types of organizations acting as CAs. Universities verifying degrees, professional bodies verifying licenses, maybe even governments verifying citizenship status or age.
So not just financial KYC.
Exactly. A user could collect these different verified attestations, represented by certificates linked to their Keeta identity, or perhaps a dedicated identity management system built on it. Then, using those privacy-preserving techniques we mentioned, they could prove specific attributes to relying parties without needing to constantly share the underlying sensitive documents or data, and without relying on giant centralized data silos holding everyone's information.
So I could prove I have a valid driver's license to rent a car online without actually showing them my license number or home address.
That's the vision. It allows users to explicitly define the trust boundaries. Who issued the credential, what specific attribute is being proven, and who is allowed to verify it. It moves control away from opaque, centralized databases and back towards the individual user managing their own verified digital identity portfolio. So if we try and synthesize everything we've covered in this deep dive, Keeta really looks like a deliberate attempt to merge the best of modern distributed systems design. thinking about cloud-scale architectures, using serverless processing concepts, employing techniques like optimistic concurrency control, and fusing that with the core principles of blockchain, integrity, security, and decentralized consensus.
Right. And the key engineering components that seem to make their claims plausible are that combination of, first, the delegated proof of stake governance allowing for adaptability. Second, that really unique virtual DAG data structure, which enables massive parallel processing through partial ordering.
Ditching the global queue.
That's exactly. And third, that client-directed two-phase validation process, which gets rid of the chaotic mempool bottleneck and provides that deterministic high-speed finality. Putting those pieces together is how they arrive at potentially achieving those headline-grabbing 13 million TPS numbers.
And KeetaNet's core comparative advantage, especially when looking at regulated industries, seems to be its ability to deliver that potential speed and strong consistency while simultaneously integrating the necessary infrastructure for regulatory compliance. That link between the X.509 certificates for identity verification and the fine-grained on-chain permissioning system is absolutely crucial. That specific combination is what could make it truly viable for global finance, where others have struggled.
Okay, so let's leave our listeners with a final, maybe provocative thought to chew on. If an architecture like KeetaNet, or something similar that successfully integrates high performance with verifiable compliance, were to be widely adopted, particularly by regulated banks, what does that really mean for the future of finance and maybe even digital identity?
Well, it could signal a fundamental shift away from reliance on purely centralized ledgers and intermediaries being the single points of trust and failure in the global financial system. Instead of one entity, one central bank, or one commercial bank's internal ledger being the absolute source of truth, you move toward a system where trust is more distributed. It's anchored in cryptographic proof, in consensus among chosen representatives, and critically, in verifiable identity credentials issued by regulated, accountable certificate authorities, but controlled by the user.
So the power dynamic shifts.
Considerably. You move from a world where trust is largely dictated by and data siloed within large central institutions to one where trust boundaries are more explicitly defined, cryptographically enforced, user-permissioned, and yet still inherently capable of adhering to complex global regulations. KeetaNet, or systems like it, are essentially offering a technical blueprint for a future where digital value transfer and verifiable identity could be simultaneously decentralized, user-controlled, highly performant, and compliant. It's a potentially powerful combination.
A fascinating glimpse into how innovative engineering might bridge the gap between the worlds of decentralized technology and regulated finance. That's definitely something to think about. And that's all the time we have for this deep dive into the KeetaNet architecture. Thanks for joining us and walking us through it.
My pleasure. It was interesting to dissect.